Okay, so what we're talking about today is 7-3 trig equations. Why we're studying this is in this lesson you're going to use algebra concepts related to trig. For example, substitution and solving equations. Substitution and solving equations. Applications include problems about blood pressure, the Ferris wheel holding pattern, projectile motion, heat transfer, and carrying the ladder around a corner. So those are all word problems related to this. Your objectives are to solve equations involving a single trig function. What we mean by that is like only sine, or only cosine, or only tangent. Okay, so a single trig function. And some of those are going to look like what we've done previously. You're also going to solve trig equations using a calculator. So on that, remember you need to be in radian mode. On the previous test, some people were in degree mode and messed up that way. So make sure you're in radian mode. Then be able to solve trig equations quadratic in form. So this sounds really weird because trig with quadratic, that's kind of doesn't go together. But think of it as like sine squared theta plus 2 sine theta plus 1. That's an example of a quadratic because quadratic for the second power. And so in a little bit you'll understand how we do that. But just think quadratic means it's a second power. We're also going to use trig identities, the fundamental identities such as the Pythagorean identity, which is the sine squared theta plus cosine squared theta equal 1. And again, we'll talk about that in a few minutes. There's other variations of this, like if you were to solve for sine squared, you'd cover this up and you'd say 1 minus cosine squared. And if you were to cover this up, then you'd say cosine squared is 1 minus sine squared. So let me write those out. Sine squared theta is 1 minus cosine squared theta, and cosine squared theta is 1 minus sine squared theta. So those are all based on the same one. So it comes from having y squared plus x squared equal r squared, where r was 1 on the unit circle. And what they're doing is they're solving for sine squared or solving for cosine squared. Another objective is to be able to solve trig equations using a graphing utility like your calculator. And again, we're about to get into the details of that. Any questions before we start? Okay, so for number 1, checking whether a number is a solution of a trig equation. What you want to do is substitute a value for theta and see whether the answer is a solution, which would be a true condition. True condition. So as a quick example on that, if you have sine theta equal 1/2, that means your y value would have to be 1/2. So you'd have something, comma, 1/2 up there, and you'd have something, comma, 1/2 right there. So those would be the two places. I won't get into more details yet about that. I want to save it for when we do the problems. But just remember sine relates to y, and since it's positive 1/2, you'd be in these two quadrants. And if it were cosine, you'd be in these two quadrants. So we want to know when it's a true solution or true condition. Number 2, this is when we want to find all the solutions of a trig equation. So this is the hardest part of the lesson. You want to find a general formula that is good for all the solutions, and then after that you want to list 8 of them. So whenever you're talking about a general solution or general formula, it's going to have k in it. Like an example is pi thirds plus 2k pi. So there's your k. Or you could have pi thirds plus 2 pi k. Those mean the same thing, but the idea is the coterminal. So if you're at pi thirds and then you loop around when k is 1, you'd still be there. So that's for k equal to 1. If you're at pi thirds and you loop around twice and stop, that would look like that. And so that's for k equal 2. You can also go around backwards. So I'm just going to do one of those. Again, you're at pi thirds, and if you go backwards all the way around, I just went forwards. Okay, time out just a second. Okay, we're at pi thirds, and instead of going this way, we're going to go around this way. So you loop all the way around, and then you go another time to right there. That's when k is -1. The negative indicates the direction, and instead of going to the right, instead of going counterclockwise, we went clockwise. So what you're going to do is substitute values for k. Substitute values for k. Notice you don't have to have a plus and minus because k is going to be an integer, which could be positive or negative. So we did a couple of cases with it positive and with it negative. Number 3, solving a linear trig equation. So that kind of looks weird right there. So why would you have how would you have a linear trig equation? Well, for sine, you remember it would look like this, and that's not linear. But what they mean by linear is it's only to the power of 1. So only to the first power. That's what we mean by linear. It's still going to be curvy and wavy. Okay, so this does not mean the graph is a straight line or not curvy. It means the exponent is 1, such as sine x. Then solve for your trig function, and then for theta. Okay, number 4, solving a trig equation. What you want to do is pay attention to the value of variables that affect the period, such as w, or shifting left or right. Then write a general formula that gives all the solutions. Then use the interval given to select your solutions. Number 5, solving a trig equation with a calculator. Express your solutions in radians to 2 decimals. Remember your valid intervals. This should also say for your inverses. Remember valid function or intervals for your inverses, like negative pi halves to pi halves for sine -1 and tan -1, and 0 to pi for cosine -1. So if you need to update those as appropriate. Number 6, solving a trig equation that's quadratic in form. So quadratic just means it's to the second power, and you may end up using u substitution, like u equals sine x, because it's the middle. And so then this would look like u squared plus u plus 1. So that's what we mean by u substitution. Sometimes it's going to be factorable, and then it's going to look like FOIL, where you do first times first, outside times outside, inside times inside, and last times last. And if it's not factorable, use your quadratic equation, which is x equal negative b plus or minus the long square root b squared minus 4ac all over 2a. So as a quick reminder about that, your coefficients on this one are all 1. So a would be 1, b is 1, and c is 1. So sometimes it's going to be factorable, sometimes it's not, and then you have to use the quadratic equation and then solve your trig equation. Number 7, solving a trig equation using identities. We want to use a Pythagorean identity or other identities to substitute so that the equation is in the terms of the same trig function. Then solve the other trig equations. So this I kind of wrote on the beginning of the paper. Start with sine squared plus cosine squared equal 1. By the way, sometimes when I'm talking about it, I don't say the x, but I'm just talking shorthand or abbreviating it. It's always like sine squared x or sine squared theta. Yeah, sure. No problem. So this would be like sine squared plus cosine squared is 1. That could be thought of as y squared plus x squared equal r squared. Okay. And so as an example on that, we have sine squared x plus 4 sine x plus 4 over cosine squared. What we're going to end up having to do on this one is you start with your identity, which is your Pythagorean identity. And in this case, remember we said if you have more than one trig function, like we have sine as well as cosine, then go in terms of sine, change to terms of sine in this example. And so what that means is we would say cosine squared x equal 1 minus sine squared x. And so then what we do is we change this to be 1 minus sine squared x. There's also a Pythagorean identity involving tangent, and there's also one involving cotangent. And I'll tell you that as we need it. But the first ones are just about sine squared and cosine squared equal 1. Keep bumping my paper. Okay, number 8, solving a trig equation using a graphing utility. You want to find the intersections on an appropriate window and then round to 2 places. Okay, so now let's fill out our header. There's your problem numbers. Okay, there's your problem numbers. I just need to do one quick correction for a second. On this one, I looped around twice, so this should have been k equal -2, not -1. It's my bad. We looped around one time and then again and then stopped. So this would have been -2. Sorry about that. Okay. So now we're working on 7.3, page 464, and our first one's number 7. What it says is two solutions of sine theta equal 1/2 r, and so then you're going to have two answers. So now what you're going to need to do is use your unit circle. That's going to be your best bet on these. So what we need to think about is it's an XY ordered pair, so that means it's cosine comma sine. So look where y equal 1/2. Look where y equal 1/2. So what that's going to look like is you're going to have something comma 1/2 there and something comma 1/2 there. And we got to figure out what those dots are. So for this one where y is 1/2, it's pi/6. And so that was square root of 3 over 2 here. So we get pi/6 for one answer. And on this one, go over to where y is 1/2, and it's a negative square root of 3 over 2. And that's 5 pi/6. I'm just going to put it here. 5 pi/6, because it's before 6 pi/6, which is pi. So that's going to be your best bet to use your unit circle, because if all you do is use your calculator in a certain manner, like if you do sine -1 of 1/2 or 0.5, all you're going to get is one answer. So this part you don't have to write, but basically calculator note, if you do sine -1 of -0.5, no, positive 0.5, sine -1 of 0.5, all you get is 0.52, which is not in terms of pi, and it also only gives one solution. And so you really don't want to use your calculator that way. We could check our one solution, pi over 6, that way, and I'm in the wrong mode. Wait, I need to do divide. Pi over 6. There's your pi 6, which is 0.52. So that checks this one, but then there's no way to know about your 5 pi 6 without using your unit circle. So using your unit circle is the best bet. Okay. The other thing I could show you is you could graph function 1 is sine theta and function 2 is 1/2, or 0.5, and then use your graphing window. So if we do this, you're going to have sine x, so that's the wavy one, and then we put 0.5, and so here you can see it crosses every time that it's red and blue at the same spot. So 1, 2, 3, 4, 5, 6, 7 are listed in this interval, but it just wanted 2 of the solutions, and it's going to want the first 2 positive ones. So use the first to positive. So you could go to Menu, Analyze, Intersect, and between here and here, that's your 0.52. And Menu, Analyze, Intersect, between here and here, that's your 2.62 basically. And so then you'd have to put it in terms of pi. So we've already done the pi 6, but I just want to show you the 5 pi 6. There's your 2.62 basically. So again, all that to say, I prefer using the unit circle, but if you want to graph it, you can try to figure it out that way. Any questions? So this is the part that you really need to write. Two solutions of sine theta equal 1/2 are pi 6 and 5 pi 6. Okay, number 8. This time we want all solutions of sine theta equal 1/2. So we know those are two unique starting points because we said start at pi 6 and loop around, and then start at 5 pi 6 and loop around. So you're going to start with the unique ones, which are pi 6 and 5 pi 6, and then you want to add 2 pi k. So that's the part you'll need to write. All solutions of sine theta equal 1/2 are pi 6 plus 2 pi k and 5 pi 6 plus 2 pi k. Just as a side note, you don't need plus and minus since k is an integer. It means plus and minus a whole number. So you don't need to say plus and minus 2 pi k. So that would give you the coterminal values. Any questions? Okay, number 9. This is a true-false question. It says most trig equations have a unique solution. True or false? So since we can do coterminal on everything, that's going to be false. False since periodic. And remember the coterminal. So just remember, you're going to have more than one answer most of the time. If it was cosine equal some positive number, you're going to have 2. If it was cosine equal a negative, you're going to have 2. Just as an example. Okay, number 10. True or false, sine theta equal 2 has a real solution. So this one, what sine theta would look like would go like that, generally. And this is where it's 1. And so 2 would be up here. And so it doesn't cross. And so it'd be false, since the range is -1 to 1. So we're only going from -1 to 1, so it wouldn't have a real solution. Okay, and then number 12. This says solve on an interval, bless you, 0 less than or equal to theta less than 2 pi. You need to watch out for your less than and equal to and your less than, so watch out for your inequalities. Pay attention to the inequalities. Because sometimes they want less than or equal to for both. Sometimes they just want it on the left side. So just watch out for that. What this question is 1 minus cosine theta equal 1/2. 1 minus cosine theta equal 1/2. And just solve this like you would normally do. One way is to just subtract 1. And so you get negative cosine theta equal -1/2. Because 1/2 minus 1 is -1/2. And then you can either multiply or divide by -1. So you get cosine theta equal 1/2. The other way to do this is if you subtract 1/2. Then you get 1/2 minus cosine theta equals 0. Some students don't like doing it this way, and that's fine. You can just pick whichever way you do it. But if you have 1/2 minus 1/2, that'd be 0. And then you can add your cosine to both sides. So you end up with the same thing, cosine equal 1/2 or 1/2 equal cosine. So now what we would do is then look at your unit circle, and this is your 1/2 with square root of 3 over 2, and this is your 1/2 with negative square root of 3 over 2. So you want where x is 1/2, and then we just look at our unit circle, so that's pi thirds, and then 5 pi thirds. So our answers are pi thirds and 5 pi thirds. So you're just going to solve it like a normal equation, whichever way you want to do it. And then from there you've got to use your unit circle. And remember, cosine relates to x, so our x value had to be 1/2. Okay, so our next one's number 16. And on this one, we have 4 cosine squared theta minus 3 equals 0. 4 cosine squared theta minus 3 equals 0. So the first thing we're going to do is add 3 to both sides. So you get 4 cosine squared theta equal 3, and then you get cosine squared theta is 3/4. If you want to skip that middle step, you can. It's basically adding 3 to both sides and then dividing by 4. But that's how it works. We would want to add first and then divide. So now what we're going to do is take our square root of both sides. So the square root of cosine squared would be cosine theta, and then we do the square root of this, so we're going to have a plus and minus the square root of 3/4. What that really means is the square root of 3 over the square root of 4, which is really just square root of 3 over 2. So if you want to abbreviate that from this step to plus and minus square root of 3 over 2, that's fine. So now what you have to do is think about every place it could either be positive square root of 3 over 2, like in quadrant 1 and in quadrant 2. So that's where it's positive square root of 3 over 2. We also have the case where it's negative square root of 3 over 2. So those are the dots or the points that we're interested in. And so then you just look at your unit circle and square root of 3 over 2 comma half, that's pi 6. This one is 5 pi 6. So I didn't draw this to scale. And then this one is 7 pi 6. And then this one is 11 pi 6. We normally just order them least to greatest, and so we'd have pi 6, 5 pi 6, 7 pi 6, and 11 pi 6. There's different patterns you can think about also on this. Like if you're just talking about your numerator, you're going from pi to 5 pi, so you're adding 4. So think add 4, then add 2, then add 4, then you add 2 again, and so forth. So that's one way you could look at the pattern. The other way is if you go from pi to 7 pi, that's like adding 6, and between these you're also adding 6. So there's different patterns you can look at for that.
Do you have to put them in order?
I think it would accept it in Math Excel, but I think it's better practice to do it. I don't think it would count it wrong, but good question. Okay, number 20. This one we have tan of 2 theta equal negative 1. This is one where you're going to do what we did on the last lesson. If you have tan, then we need inverse tan to both sides. So tan negative 1 of negative 1. To get tan negative 1 of negative 1, think about what that would mean. We know tangent is positive where both are positive or both are negative. And we know tan is negative in this quadrant and in this quadrant. We also know that it's 1 when it's exactly at 45 degrees, like when it's the exact same numbers, and in this one it's just a negative. So this one's going to be your answer at 3 pi fourths. And this one would be at 7 pi fourths. So that's as far as what tan -1 of -1 is. The tricky part is some students say, well, that's my final answer. But we have 2 theta equal to that. So what we have to do is we need to handle our cases. We have 2 theta is equal to 3 pi fourths, and we have 2 theta equals 7 pi fourths. So what you're going to do is divide by 2, or you could say multiply by a half, and so then you get 3 pi eighths, and on this one you get 7 pi eighths. So 3 pi eighths and 7 pi eighths. The next one is an easy one, cosine theta plus 1 equals 0. So you just subtract 1. So cosine is -1, and that happens at -1 comma 0, which is at pi. So your answer is pi. And then our last one is number 28. We have 5 cosecant theta minus 3 equal 2. We're going to add 3 to both sides, so we get 5 cosecant theta equal 5. So we're adding 3, and we get 5 cosecant theta equal 5. Then we want to divide, so we get cosecant theta equal 1. And remember, when we had this type question, we took the inverse of both. So the reciprocal of cosecant is sine, and then the reciprocal of 1 is still 1. So all we want is where the y value is 1, which happens right there, and that's pi halves. So pi halves is your answer. That's going to be our stopping point for today.